who will speak about interesting, very interesting stuff about computerized Somos sequences.
Okay, thank you very much, Dr. Z, for inviting me to speak. So we're going to start off by looking at the Somos-4 sequence. And so this is a sequence of numbers that we start off by, we define a sub 1 is the same as a sub 2. We start off with 4 1s at the start. And then after that, every term is 4, so for n bigger than 4, we go with a sub n is we take a sub n minus 1 times a sub n minus 3 plus a sub n minus 2 quantity squared. And all of that, then we divide by a sub n minus 4. And so this is clearly going to give us some sequence of rational numbers. This rational number here, give us a rational number. But let's actually calculate out a couple of the terms. So we have, a sub 5. Let's write out let's do some of these terms. A sub 5 is a sub 4 times a sub 2 plus a sub 3 squared over a sub 1. So that's going to be 1 times 1 plus 1 squared over 1. That's 2. A sub 6 is a sub 5 times a sub 3 plus a sub 4 squared over a sub 2. So a sub 5 is 2 times a sub 3 is 1 plus 1 squared all over 1, and that's 3. A sub 7, we can keep doing this. 3 times 1 plus 2 squared over 1 is 7. A sub 8 is going to be 7 times 2 plus 3 squared over 1 is 23. So far so good. I mean, we've kept the first 4 terms are always going to have one of those initial ones dividing it. So there's no surprise really that of anything that we've gotten so far. But the first surprising one is a sub 9, and so that's going to be 23 times 3 plus 7 squared all over 2. Well, that's 118 over 2, which is 59. And even more surprising, a sub 10 is going to be 59 times 7 plus 23 squared over 3. That's 942 over 3, which is 314. So let's stop for a second and catch our breaths and realize, we've gotten awfully lucky when doing this calculation for a sub 9 and a sub 10. This 2 divided 118, so we got an integer here. This 3 divided 942, so we got an integer here. And so back in the 80s, Michael Somos, who was actually visiting here several weeks ago, he was playing around with not quite this sequence, but a related sequence, and realized you're always getting integers. And the question is is this always true? Can you prove this? And so sure enough, proofs were found. There's several different proofs that you can do to prove that the Somos-4 sequence is integral. And so sure enough, it's in the OEIS Sloan's. So it's A006720. So this is what's called the Somos-4 sequence. And so more generally than the Somos-4 sequence, we can have Somos-K sequence. And so we define, for example, the Somos-5 sequence. So note that the Somos-4 sequence, it's the order of the recurrence, it's fourth order. You look at the previous 4 terms to figure out what your next term is going to be. And so the Somos-5 sequence is a fifth order sequence that's defined in much the same way. So once again, we start off with all 1s, and then you have a sub n is a sub n minus 1 times a sub n minus 4 plus a sub n minus 2 times a sub n minus 3 all over a sub n minus 5. So basically what's going on here is so the pattern is kind of like to recreate these Somos k sequences, you define by a sub n minus k, whatever that is, and then you have a sub n minus 1 times a sub n minus k plus 1, and then a sub n minus 2 times a sub n minus k plus, so on. So, you work your way together. So when k is even, you're going to end up with that squared term, so a sub n minus 2 squared. And so sure enough, the Somos 4 sequence, I should point out, so there's another way that we can write this that I'll sometimes use. So a sub n times a sub n minus 5 is completely equivalent. It's a sub n minus 1, a sub n minus 4, plus a sub n minus 2, a sub n minus 3. And so sure enough, you get, I'm just going to delete the initial ones. An interesting part goes 2, 3, 5, 11, 37, so forth. And of course, this is in Sloan's, right next to the previous one.
Wait, sorry, what was this latest sequence?
This is Somos 5 sequence.
Yeah.
So it's defined this way, and we start off again with all ones.
Right, and you're saying that, so when you do that, those are the values that you get?
Yeah, and so once I should have said this, but yes, it does turn out to only give you integers. It has the surprising integrality property.
What are some more terms?
So let's see, how many did I write down? I got 37, 83, 274, 12, 17. That's as much as you're going to get from me. And so then people came up with the natural analog for Somos 6. And once again, this property held. Somos 7, this property held. Somos 8, it doesn't hold anymore. And so it's kind of weird that Somos k only gives you integers between k equals 4 and k equals 7. K equals 3, no, it's kind of see at the bottom, right? Is that no? Oh, k equals 3 is a kind of stupid case, just because of let's see what Somos 3 would be. So you get a sub n minus a sub n times a sub n minus 3 is a sub n minus 1 times a sub n minus 2. Okay, start out with all ones, you're going to get all ones, so nothing much going on there. Okay, so one important thing about that we can see from writing in this form is that this equation is totally quadratic. Every term here is a quadratic term. Same thing, we written that in the corresponding form. It's very much a quadratic term. Excuse me, a quadratic sequence. But what happens if we change it so that we aren't looking at only quadratic terms that are recurrence anymore? What happens if we have, say, linear terms? And so here we come with the Dana-Scott sequence. And so this is probably experimental math at its finest. So we start off with a sub 1 equals a sub 2 equals a sub 3 equals a sub 4 equals 1. And then after that, a sub n is defined by a sub n minus 1 times a sub n minus 3 plus a sub n minus 2 over a sub n minus 4. And so, thanks. Does anybody see what's different about between that and the Somos 4 sequence?
Yeah, it's not squared.
It's not squared. And as legend goes, Dana-Scott, he wanted to write a computer program to calculate Somos 4 to investigate for himself, and that was a typo. He accidentally left off the squared term. And so I think this is one of the nicest examples of like experimental math. Like lots of times, how often in the sciences do you have an example of somebody makes a mistake, and then it's like you're adding two chemicals together, you add too much, oops, but you get something useful out of it. Well, this was a case of some sort of mistake ended up leading to something useful.
Yeah, famously penicillin, the serendipity, mistake.
Yeah.
The coincidental.
Yeah. So we have, so the Dana-Scott sequence starts off, so after all ones, 2, 3, 5, 13, and then 44 over 2 is 22, and 123 over 3 is 41, and so on and so forth. So here we've moved into talking about, so now our recurrences, as we said, they aren't purely quadratic. They also can have linear terms in them as well. So then, back maybe about, I forget, 6-8 years ago, we had a new family of Somos-like recurrences. And this is due to Heidemann and Hogan. And so this is Rutgers' very own Emily Hogan, who just graduated here just over a year ago. And so they came up with new recurrences that are going to mix together linear and quadratic terms. And so the one that they found in the original paper, they had a sub n times a sub n minus k is a sub n minus 1 times a of n minus k plus 1. And then, so we have one quadratic term with two linear terms. A of n minus k minus 1 over 2 plus a of n minus k plus 1 over 2 for k. So just for example, if k equals 3, you get a sub n times a sub n minus 3 is a sub n minus 1, a sub n minus 2, plus a sub n minus 1, plus a sub n minus 2. And this is the sequence. We start, again, we're always starting off with all ones. 1, 1, 1, 3, 7, 31, 85, so on and so forth. So once again, this is another example of a sequence that surprisingly turns out to be integral. Then let me just note, Emily went on in her PhD thesis. One of the chapters dealt with this, and so she ended up doing even more with this. So this is just, there's only one parameter floating around here, k, and she actually found families with lots of parameters. So define a sequence b sub n times b sub n minus k is b sub n minus I, b sub n minus k plus I, plus b sub n minus j, plus b sub n minus k plus j. And so this is integral if the following conditions hold: k even and I odd, j is k over 2, I even, and j is I over 2, or j is k over 2, or j is k minus I over 2. And so, and then there are also corresponding ones for k odd. I won't take the time to write those down. But now, this is very cool because now we have lots of parameters floating around. And in her thesis, she proved that these all give you integral sequences. So clearly, it feels like there's something going on here.
Are the positive of it?
I don't. Every term is positive.
Yeah. In the Somos case, it's also positive.
All
the proof.
All of those.
In Emily's case.
So if you move this downstairs, then that's going to be positive number over positive number is something positive. The trickier thing would be the Laurent phenomenon, which I haven't talked about yet. So that's where I don't know if she proves strictly positive.
Sorry.
Yeah.
The positive is obvious.
Yeah. So Dr. Z actually kind of is segueing into my next point here. And so it's like, okay, people came up with lots of various ad hoc techniques to try to prove that that these sequences were.
What's also got me stopped? The Laurent phenomenon, and then within Laurent phenomenon.
Yes,
you have
yes.
integrality, and
Yes.
you have, but this of course is obviously positive.
Right,
That was
right.
a stupid question. Yeah.
So there are lots of different ways. So Somos-like sequence, one of the nicest proofs is just by a straight like modular arithmetic argument. You're always trying to show that a sub n minus 1 times a sub n minus 3 plus a sub n minus 2 squared is congruent to 0 mod a sub n minus 4. Let's see, for Emily's stuff down here, she showed that her sequences they satisfied like a linear recurrence which may have been of a very large order, but it was a linear recurrence, and so from that she was able to show integrality. One of the slickest proofs that I've seen with like these Somos sequences, actually, there are nice combinatorial proofs where you can actually show that they count the number of perfect matchings in a sequence of graphs. So, and once you do that, obviously it's integral. And positive. Yes.
Yeah, but it's always positive. So.
Yes. But those always kind of seem like ad hoc methods. Like, you know, it might work for one, but not for others. And so the question was always like, can you come up with some nice unified technique that would in just about every case work? And so the answer is yes. It won't work in every case, I don't think, but it does work in many, many cases, definitely for every case that we've come up with. And so actually, we're going to pass to something more general than just the sequences being integral. We're going to show that they have what's called the Laurent phenomenon. And what the Laurent phenomenon says is that if instead of setting, so I lied at the start when I said we're always going to set everything equal to 1. So we're not going to set the initial variables equal to 1. We're going to treat them as formal variables. Then the sequences. So every term of the sequence will be a Laurent polynomial in the initial variables. And so what that means is that you can have whatever you want in the numerator of your fraction, but downstairs has to be a Laurent monomial. So you can have a1 times a2 squared times a3, but you can't have like a1 times a2 squared plus a3 in the denominator. So you can have like a1 squared times a2 plus a3, a4 squared over a1, a2 squared. This is a completely okay thing to come out in our sequence because this is, or downstairs is just a nice Laurent polynomial.
Is it a monomial? Is it a monomial?
Yes, it's a nice polynomial.
Yeah, it's a monomial.
Yes.
It's a Laurent polynomial.
Yes.
Laurent polynomial is a polynomial divided by a monomial.
Yes. But when we have this plus sign here, this doesn't work anymore. And so, do you guys see how this property immediately implies integrality of the corresponding sequences? So the corresponding sequences, when we start with all ones, we're going to set a1 equal to a2 equal to a3 equal to so on and so forth equal to 1. So we're going to plug in 1 for each of these. And so obviously both top and bottom are going to be integers, but the downstairs is always going to be 1. It's going to be a product of a lot of 1s. And so that instantly implies that, so the Laurent phenomenon instantly implies that our sequence is going to be all integers. Is that making sense so far? So we're looking to prove the Laurent phenomenon, and fortunately, there's these nice heavy-duty algebraic machinery that's been laid for us that will make doing proofs pretty. There's a very nice algorithm for churning out proofs, basically, and so Thoman and Zelebinsky they came up with criteria which they're sufficient, but I don't think they're necessary for showing that our sequences have the Laurent phenomenon. So let f be a polynomial in x1 to x sub k minus 1, and consider the recurrence defined by a sub n times a sub n minus k is f of a sub n minus 1 to a sub n minus k plus 1. So in our Somos 4 example, then we're going to have k is 4, and f is going to be x1 times x3 plus x2 squared. Because the top up there, a sub n minus 1, that a sub n minus 1 becomes x sub 1, a sub n minus 3 becomes x sub 3, a sub n minus 2 becomes x sub 2. So then, after we start out with this definition, they run through, the next part is just like all these definitions of polynomials, that it's kind of tedious, but the nice thing is at the end, it gives you a very automated way to prove integrality. So we have, so define q sub m is f of x sub m plus 1 to x sub k minus 1, 0, x1, x sub n minus 1. And so basically what we're doing is we're replacing x sub I with x sub m plus I, and then you take that mod k, and then x sub k minus n gets replaced by 0. So let's actually calculate out what QM is in the Somos 4 case. So we want to find Q1, Q2, and Q3. And we're going to use F is x1, x3 plus x2 squared. So Q1 is going to be, so M here is 1, so we start with x2, x3, comma 0. Making the appropriate substitutions into that gives us 0 plus x3 squared. Q2 is going to be x3, comma 0. So here this was 2 plus 1. Gives us, starting with x sub 3. x3, comma 0, comma x sub 1. And that's going to be x1, x3. And then q sub 3 is f of 0, x1, x2, x1 squared. And then to finish things off, so we're just getting started with the whole definition of polynomials. We have another bunch of polynomials coming up. And these are, we're going to call them G's. So define sequence of polynomials g sub k minus 1 down to g0 by First one, g sub k minus 1 is f, and then g sub m minus 1 tilde is you take g sub m and you replace x sub m by q sub m over x sub m. G sub m minus 1 double tilde is you divide by Laurent, some sort of Laurent monomial that makes, so we're going to make it not divisible by any xi. Make it, let me say, it needs to be, so we're going to turn this into a polynomial, and that's not divisible by any xi. And then g sub n minus 1 is g sub n minus 1 double tilde over, you divide out by qm to the b, which is highest power of qm that divides g sub n minus 1 double tilde.
What's capital L?
So this is a Laurent monomial that the goal here is we want to make this whole, we're basically start off with g sub n minus 1 tilde. We want to make it so that it's a polynomial, so we have to divide, so we have to multiply by anything that we're dividing it by. And then we also have to make sure that we're not dividing, that there isn't any x sub I that's a factor of the whole thing. So in just a couple minutes, just a minute, I'll do an example, and then you'll see what's going on. And then the punchline is that so theorem is that, so Homan and Zelevinsky is that our sequence has the Laurent phenomenon if the following holds: f not divisible by any xi, and that's easy enough to check. Each qm is irreducible element of z adjoin x1 to the plus minus 1 to xk minus 1 to the plus minus 1. And then finally, here's the big one, is that g0 equals f. So when you run through all of the calculations, I mean, like this whole nasty sequence of calculate out all of these polynomials, the punchline is, at the end, you want to get f. Which is what you started with, because g sub k minus 1 is f. And so if after all of these calculations you get back what you started with, then you have the Laurent phenomenon. So let's do an example, and we've already used it plenty of times so far. So we are going to, but let's go ahead and calculate out all of this stuff for Somos 4. So for Somos 4, well, we already, let's see, what do we have so far? Well, we know that f is x sub 1 times x sub 3 plus x sub 2 squared.